So let's look at how we can use conservation of energy. All right. So let's look at this problem. So we've got a motorcyclist. He's trying to leap across a canyon by driving horizontally off a cliff. When he leaves the cliff, the cycle has a speed of 38 meters per second. We want to know what is the speed that the 150 kilogram cyclist is going to have when he strikes that other side of the canyon, which is at 35 meters. All right. So previously, when we did this, we would have to do that projectile motion stuff, right? So we would have to have, that's what I want. We'd have to have v equals d over t. We'd have to use the v equals gt, and we'd have to use the d equals 1/2 gt squared, right? And we'd have to go through and find the time and all that other stuff, right? And projectile motion's a little tedious. It's a little difficult, okay? But now with energy, we don't need that, right? With energy, it's pretty simple, right? As long as we identify our stuff and we plug it into the right place, it's just straight algebra, and it's very quick, all right? So here's what I've done. I've identified things that we know. We know that he drives off the cliff with an initial speed of 38 meters per second, and that the guy and the motorcycle together have a mass of 150 kilograms. Okay. Looking at our picture, his final height is going to be 35 meters. That's where he's going to land. And he drives off a cliff that's 70 meters high. And we want to know how fast is he traveling when he lands. Okay. And here's the path that he takes when he goes. So if we think about this, he's 70 meters high. What type of energy does he have just from being on top of the cliff like this? He's got potential. Excellent. All right. But he's also driving at 38 meters per second. So what type of energy does he have from that 38 meters per second? Kinetic. He's also got kinetic. All right. So he has potential and kinetic before he drives off the cliff. So you told me he has potential and kinetic before he drives off the cliff, right? So you're telling me that he's got some sort of total mechanical energy, right? PE plus KE is total mechanical energy, all right? And the sum is equal to the potential and the kinetic. Yep?
How do you figure out how much the potential?
How much they are? Through the equations that we know already. And we're going to plug that in, you'll see it, okay? All right, so now he goes flying off the cliff, and he lands on the other side. He's at a lower height, but is he still at some sort of height? So he still has what? Okay, he's still got potential. Now, what's going to happen to his speed as he drives off the cliff? He's going to go faster, right? Because he's falling, so he's going to pick up speed. So because he's going to pick up speed, he should also get some kinetic. Okay, so then we have here PE final plus KE final. All right, so let's plug in what we have, what we know. We know that the equation for potential energy is mgh, right? So it's just m times g times h sub I. Plus, the equation for kinetic energy is 1/2 mv squared. It's just 1/2 m v sub I squared. And that's equal to mgh sub f plus 1/2 m v sub f squared. So all we did here was we just plugged in the information that we already know, right? Or I should say, we just made substitutions for our equations. Now we can plug in what we know. He's got to, actually, before we even do that, does there seem to be a common term running through there? What is it? Right, so every term has a mass, right? Every term has an m. So could we plug it out? We could take it out and we could actually cancel them. Because every term has an m, they cancel out. Just makes our life a little bit easier. If you're going to do this, make sure that every term has that m. Don't just automatically go wholesale and wipe it all out. You have to make sure that everything has an m before you do that. Okay? I don't want you to drop an m and then realize you needed it later. And it throws everything off. So g is 10. H sub I, the initial height was 70. Then we got plus 1/2. The initial speed was 38, so that's squared, equals 10. The final height, that lower cliff, is going to be 35. And then we've got 1/2, and we need to find that v sub f squared. Okay. So again, we're just doing straight algebra. There's nothing too difficult about this in terms of where, as long as you can identify what it is that you have, you can plug it into this equation and you can solve for it pretty quickly. So 70 times 10 is 700. 38 squared. Anybody get a calculator real quick? 38 squared. That's some big number. And then I think it's 722. When you take half of it, it ends up being 720. So 1444. All right, so 38 squared is 1444. Half of that gives us 722. And then 350 plus 1/2 v sub f squared. Okay, so we've got 1422 equals 350 plus 1/2 v sub f squared. So we're going to subtract now 350, right? We'll subtract 350 over to the other side, so that gives you what? 1422 minus 350 is what? What do you got? My calculator peeps. So 1422 minus 350. 1072 is equal to 1/2 v sub f squared. So if we double that, we get 2144. Does that sound about right? Right? If I take this 1/2, multiply both sides by 2 to get rid of this half, we should get 2144, right?
Yeah.
Okay, and then to find out what v sub f is, we need to take the square root of that. And that is what? Square root of 2144, 45 something? 46.3. And that's meters per second. All right, so let's look at this. So he goes from this height, 70 meters, and he's traveling at 38 meters per second. And he falls down to 35 meters, and we just found out he's going 46.3. All right, so let's think about what's happening. What is he losing going from 70 to 35? All right, he's losing potential energy. But what is he gaining from going from 70 to 35? He gained kinetic, right? Because he went faster, right? So if you took these two, right, which it would be 1422, this side would have to be 1422 as well. So he started with initial amount of energy of 1422. He ended with an final total energy of 1422. The numbers are the same. We just changed the distribution of them. Okay, does that make sense? Does this seem a lot easier than projectile motion? Right, so it's pretty nice, right? Energy is really, really powerful. It's nice because it's simple, but it's really powerful. Okay, does it make sense? Okay, cool.